All right, so this will be a review of what we will be talking about for the final. We have this notebook here that I am sharing on my screen from the questions that we might expect for the final. So with that, did anyone have questions prepared as it relates to what we should be focused on?
I'm kind of hoping we could go through the concepts in an organized fashion, kind of down the line. Maybe that's a lot, asking for a lot, but I was hoping to go through those in an organized way where I could take notes.
Is there a specific concept that you feel we should focus on?
Well, I was very interested in reviewing, I think it was Simpson's paradox, because I don't remember a discussion of that in the homework. But there are several of these kind of bold red highlighted areas that I think it would be nice to just learn what specifically you want us to focus on those areas.
Okay, sure. So you were referencing not these topics I have on my screen, but these topics.
Yes.
Cool. Okay, so yeah, we can definitely start with Simpson's paradox. Let me actually grab the slide that was from the last chapter, which we kind of breezed through faster towards the end. But this is more so I want to expose the class to a lot of the limitations in any of this type of analysis, especially hearing if you're applying it in your work environment, it's important to know the constraints of these tools we're applying. So Simpson's paradox at a high level is when we take a large data set like this one in green of just, this is a scatter plot of something like pasta intake and what your BMI is. And when it's not going so fast, this green one shows that if you don't split this data in any type of categorical way of like making groups, which is what we're doing in Anova, is like we're trying to use some type of category to understand how the variance changes between groups. So this is just an example of how it could skew the actual pattern that makes more intuitive sense too. Like at the end of the day, it's really important to think hard about what it is you're seeing. And if it doesn't make sense to you, it should be questioned further. So this is just an example of when you create different groups and stratifications, as if you were trying to sample from different clusters here, you would actually start to see a negative trend, which wouldn't make sense of if you're intaking more pasta, you know, your BMI would go down. So just connecting back to this link, because this just shows it a little bit further with like an interactive example. And it's pretty much just saying when you start to use something like age to change different things, it can skew the results that you're seeing. So in short, when you start to use categories in a data set, you might be changing how the relationship really is in the two variables that you're really looking at here. Does that make sense?
No, not yet.
Okay, let me grab, I have another, there's a really good example from Titanic. I will grab that. But for the scope of the final, it would more so just be if you can explain how when we create different categories in a population, we might be capturing different patterns that might not be reflective of the entire population. So let me just grab this. Oh, this is the one I wanted. So really, it's very high level. You don't need to necessarily worry about the details. This is just a really nice demonstration from Wolfram alpha that shows, oh, why is this going so fast? Okay. Let me just take a screenshot because this is what I want to show. And this just relates to some of the pitfalls. That's really all it is. I just want the class to understand that there are pitfalls to what we're doing, and Simpson's paradox is one of them. And this is perhaps a better example than the diabetes, where if you were to look at who survived the Titanic and you perhaps just based it off of, let me think back to this example just so I can talk through it a little bit better. Oh, this is from Carl Heiner. This was who I studied the statistics with back at SUNY New Paltz. That's why I know about this. That's great. So it's just talking about how the pooled data is misleading, where if you look at, I think in this case, it would be like gender here. I think that's what this example is getting at. If you kind of looked at the difference between, so if this was like an Anova test and you were looking at categories of, predicting who would survive the Titanic based off of perhaps something like gender. And then if you looked into like the different classes, you'd be able to see just a difference in survival rates. Like it's just saying when you slice and dice the data in different ways, and sometimes if you're using this to manipulate patterns, that's why I use the diabetes one, because that was almost deceptive in how it did it to find the exact opposite pattern. Really, all this is saying that it could find relationships that aren't reflective of reality. So I can link this to the final review because I would just check out some of these other ones. To talk through it more. Did that help a little bit more to explain it?
I think you're saying that populations assessed are not necessarily reflective of the entire populations, that we shouldn't make too many assumptions or inferences about single data sets and how that reflects the entire populations. Is that correct?
It's more if you take an entire population and create categories, say just based off age, and look at each of those age patterns, that might not necessarily be reflective of the entire data set and like the real patterns that might exist underlying. So it's really just about how when we create these categories, we might be splitting the population in ways that doesn't reflect the real patterns in the population, because we are looking just at each separate group rather than the entirety as a whole. And this is just an example of this paradox of if we do it in a way that changes the results of what really happens in reality, it's just something we need to keep in mind. So it's just really key points is just when you are finding your analysis, if it doesn't make intuitive sense to you, like just this BMI example, if this is just an example of the statistics might say, hey, this is a relationship, but you shouldn't always trust that.
So the paradox is we're studying something, but we can't overassume anything about our findings. Is that the paradox?
Exactly. Yeah, okay. to a sense.
So it's a theoretical consideration. That's what Simpson's paradox is.
I think that would be an appropriate way to refer.
Okay. And this is also linked with sampling bias as well. Like using sampling to make assumptions and being careful about that.
Exactly. So that's why I listed it as an item, because it could be relevant to one of these questions that we have here. of, sample bias. It is related to like, how do you make a sample that's representative of the population? So, and I would recommend reading into it a little bit more. And I must admit, I should read into it more to be able to explain it a little bit better. But it's just a pitfall of when we try to sample from a population and create categories. This one's specific though to Anova, when we create these arbitrary like bins and look into each of these different interactions within the population, and like those different interactions, just because they're in this specific bin, like that example here with, I think that these were different ages in the different stratifications that they made. Like if you just look at age, there's actually this downward trend in BMI, but that's not reflective of the entire population. So I would just recommend reading through what I linked here, because it showed probably better than I just explained it about this pitfall.
Okay, thank you.
Can we go over the null hypothesis and the alternated hypothesis, and how we're supposed to find them again?
So to go over the null and alternative, and then how do we find them? These are the two separate? I feel like, yeah, two separate questions, perhaps.
Well, yeah, not how we find them, I should say. Can we just go over the concept again?
Sure. Yeah. So the way we should think about the null and alternative hypothesis is pretty much when we are trying to prove something, we need to first state the current state of being. And our goal as, researchers and analysts is to find evidence to support whatever new finding that we are thinking about. So, but getting that back to what we do for our class, because I know that's a little abstract, and talking about the jelly beans related to acne doesn't necessarily relate to when we would test something like this. But just for example, if we're trying to, I guess, let me talk through a couple different hypothesis tests and maybe give some examples, because they're hypothesis tests where we're just trying to see, are the means similar between these groups? And you kind of can just use the same framework for any of those questions, and we don't need to think necessarily too much about it. When we need to do more of an assessment is more so if we're trying to compare like proportions, saying this one is larger than that one, or saying, is this equal to a specific value? If I made the claim that the average, housing price in New York was, $100,000, that would be a statement that we now need to test. So something like that, we would do something. Let me grab an example. Yeah, because I'm just looking for when the mean is equal to a certain value, which would actually be this first one that we're looking at. Not equal to, but if I were to say, the average housing price in New York is greater than 100,000, maybe this would be a better example. So you would want to pretty much state the opposite as the alternative, because that's what we're trying to find evidence to prove. And the null is this default level of what we are trying to find evidence to disprove. So this null hypothesis would be, for that example of New York, housing prices, and if I were to say it's greater than 100,000, are null hypothesis is actually that it's less than or equal to 100,000. And we're trying to find evidence to support the alternative to say that the mean is actually greater than this value, which is my conjecture that I'm trying to test. And so you would then try to take a sample of housing prices in New York, and create an experiment around it and make sure that sample is representative of the population and actually test if that mean differs to a degree that's significant using our hypothesis testing framework in order for us to either say, no, we didn't find that average mean is far enough on that distribution curve to say with a degree of certainty that it is much greater than what we're trying to prove. And that's when we would reject the null hypothesis if we did find that the average price of a house was significantly greater than what we would expect to see if that wasn't the case. So that's why we're testing the mean and seeing like how far away from the distribution. So that's how it relates to the test statistic and our p-value. So we're comparing those two statistics in order to conclude that the mean housing price is indeed greater than this value, or we didn't find it to be that extreme, and therefore we can't reject the null hypothesis.
I have a
Did
quick
that
question.
help? Yeah, sure. But also,
So-
just before, I don't want to, Darren, did that help answer your question? I just don't want to get on a tangent too much before.
Yeah, that explains it. Thank you.
Okay, great. And
My question was about that, the null hypothesis and the alternate. So like, basically when the researcher says like, or the analyst says, oh, they believe something to be true, and it's like, I don't know, like what you said with the houses. Is that the alternate? Because they're trying to prove what they believe, and then the null would be opposite?
exactly.
Okay, thank you.
And just relating that back to an example we've used in the lectures of you're like a judge trying to prove someone guilty. We start off innocent until proven guilty, and your role, perhaps as a defense, I don't know, law thing. So whatever that role would be, you're trying to find evidence, to prove someone guilty.
So even if the original statement is like this, let's say these things are not equal to each other, we should still make it a positive statement as the null hypothesis because we don't want to negate something as our null. Is that correct?
So if I understand the question, if we were just trying to prove that these things are not equal,
Yes.
and I am questioning if that would be a valid hypothesis that we can really test using this framework, really, because all we have is these probability and distributions to pretty much compare means.
Okay.
And I don't think you can really do it in the opposite way if we're
Okay.
trying to say these things are not equal. So you'll never really, at least I would, please, if anyone wants to do this research, and I'll look into it further myself, but you shouldn't expect to see not equal in the alternate.
In the null.
Yeah, well, yes,
Okay.
yeah.
Okay. And then when the response is we fail to reject the null hypothesis, that's like a brain twister for me. So can you just unpack that? Like failing to reject a null hypothesis?
Yeah, it is jargon, but it's jargon for a reason, because of, actually related to your other question, it's because we did not find enough evidence to reject our null hypothesis. So that's why it's saying
we agree with the null hypothesis.
yes, that would be a lot easier to say, but it's
Yes.
kind of like we're not necessarily making that conclusion with what we did. It's just what we tested. We failed to reject the null hypothesis.
Got it. So
Yeah.
that means we agree with the null hypothesis.
Yes, definitely you can think that way because that is what's going on.
Okay.
But I think the jargon is important here, and that's why I wanted to use it for our class. But yes, for intuitive understanding, that's exactly what's going on. These are great questions, by the way.
Paul has a question in the chat. I don't know if he was able to see it.
Okay, let me check now. Okay, I also see there was another question from Paul that I didn't answer. Okay. Okay. So I'm just looking at all the questions now. So I'll just start from the first question and then we'll work our way down because I see there's a bunch from Paul. And yes, thank you, Darren, for pointing this out to me. Just the first one, because we didn't talk to this. I'm curious how this test will compare to the midterm with a longer written component. Paul, did I answer that question a little bit, or would there still be more context to answer there? Okay, great. Okay, so the other one that we were talking about, focus. Okay. I'm reading this other question. My questions mostly focus on the concepts rather than the code itself. Like you said, how can we interpret and apply them to real life? I think that would be good to talk through, and then we can talk through this p-value one next. So something like applying to real life. In a case, I think, some of these tests are pretty much just like the start of any type of analysis, and depending on, what is the business question at hand, there likely would be further analysis necessary. But really the purpose of some of these hypothesis tests, and I think specifically when we get past just testing if the means are different, but something like, let's talk through a couple of those of like, how would this relate to real life? Maybe even all of these, because I think that's really important. So even just something like this question, if we're trying to test if the population variances differ at this degree of significance between blue chip and index related funds, where that might relate back to a business decision. If you're an investor and you want to know which portfolio has more risk, because perhaps there's just more variance, and maybe there actually isn't any difference in the variance between these two funds based off of the sample that's representative of the population. So perhaps you would be able to make that decision of, it doesn't necessarily matter if I use blue chip or index, they're both pretty volatile in the similar way. But perhaps a hypothesis would be that the index is more volatile than blue chip, and we can actually test that. So it does depend on whatever it is you're trying to answer. But using this type of framework, we can start to understand how things compare to each other. And that's probably a lot of those comparing of the means, comparing of variance types of questions that really only gets you that far. Or if we're trying to, similar to what I was talking about, prove that the average price is this, we can use these types of testing frameworks to answer that and prove it. But getting into some of the other more just different tests specific to the chi-square test, something like this, where we're looking to see if two variables are independent of each other, that gets into like a whole litany of different applications. besides just knowing, are these two factors influencing each other? That could be related to perhaps like a whole model that you might want to create. If you were trying to predict something, you want to know, are these two things independent of each other, or does this cause that? So this type of contingency table that we create, where we're trying to just see based off of the probability of how often this pattern or this observation showed up, that it created this pattern of frequency differences between these two different groups in a way that is, you know, significant using this chi-square testing, which is similar to those other hypothesis testing frameworks, where we're really just trying to see, is this so far from what we would expect that it's significant? And something like this could be used to say, you know, that if the light condition is day, you're more likely to actually have a car crash. Or, you know, is there no relationship between these two variables whatsoever? So thinking to other use cases, if you were trying to test, you know, for housing, again, if you're trying to say, like, would a 1-bedroom house give me, you know, a larger return on my investment compared to anything that's not 1 bedroom? We could use this type of analysis to just see, is this like independent of another category? And then lastly, talking through Anova, which we have this interaction of, let's just talk through like a one-way Anova, where we would be able to see by different categories in a population, or the sample we're taking from that population, if there is any type of difference in the variation as it relates to like a target variable. So it kind of goes a step beyond just testing, are the variances different? And it's looking to see, are the variances different as it relates to this type of numeric value that we're trying to understand better. So in this example, it was something about production rates for different assembly types. You know, could we actually prove that one assembly is better than the other using the values that we would see from an experiment? So even if you were getting back using like a housing example again, because that was the data set we used on the midterm, so I know you're all familiar with that. Thinking about how we wanted to maybe compare between states and say, is housing more expensive in New York compared to Connecticut, or maybe California compared to New York? Like, how do these two places compare as it relates to this specific target variable? So any further questions relating to how this might apply? But I would also encourage you to think about other ways beyond what I'm thinking, because I'm sure there's lots of others that I haven't thought of.
Is that the right answer from like the homework?
Oh, this is all from the solutions from the homeworks. I just compiled the questions that I recommended to focus on into this notebook.
When can we expect our homework grades?
Yes, I've prioritized putting the solutions so that you can essentially grade yourself and know what you got wrong, and kind of, you know, at a high level, know what you might expect to receive as a grade. And you can expect to receive your grade pretty much after this weekend, when I will be very focused on getting all those grades done. Is there a specific concern about homework grades?
No, just the last 2 or 3 chapters kind of, I just made a go at it, but I'm really not quite sure how much of it I did well. So just kind of hoping to gauge from the homework analysis, just kind of like where I need to focus on for the final.
I would recommend reviewing the solutions. That's why I always try to make sure every week the homework is due, that the solution is there. I do try to give a little bit of leeway for some students who might have not gotten it in at the due date and will get a penalty, but still wanted to submit it. But I don't want to release the solution before that point of time. So that's why sometimes it's not given exactly right after it's due. So I would recommend just looking through the solutions, because I'm pretty lenient with answers for the homework. I'm not looking for correctness. I'm looking for the approach you took and is it logical and consistent? Because at the end of the day, there's never really like one correct or right answer to a lot of these things. It's more so, is your approach rational and are your conclusions reasonable? So I don't think you can really use the grade per se as like a proxy sometimes, because you might not have gotten the correct answer, but as long as the approach that you took was logical, that's what I'm looking for. And for captions on your graphs as well, like I'm looking for the interpretation and how things are understood. Does that help answer that question?
Yeah, I know to expect the homeworks after the weekend, so that's okay. Thanks.
So
Oh.
for the written part, how long are you expecting the answers to be? Like an essay per question, or like a little smaller than that?
Really, I'm just looking for conciseness. So I don't think it's a little bit different of a format compared to the midterm, where I have like specific bullet points of what I want you to answer. It's more so, did you answer this? And is there evidence of your answer in what you respond with? So definitely not looking for a paragraph if it's not necessary. It's more so, this is my answer. This is how it relates to my analysis. But it also kind of depends on the question, something like, explain a type 1 and type 2 error as it relates to a hypothesis. It doesn't need to be super detailed. It really should just be more straightforward in answering the question.
Well, that being said, can we go over that part?
Oh, so this type 1 and type 2 error?
Please.
Yes, of course. So talking through type 1 and type 2 error, and this relates to a lot of things in any type of like test or like model that we're creating. We always want to check if we got it right. You might be creating some type of experiment in your lab, but really at the end of the day, it matters more how it performs in the field. Like, how does this actually relate to what I'm trying to solve? So this has applications outside of just our hypothesis testing framework, but within, the narrow scope of our class and hypothesis testing, a type 1 error relates to if we were to reject a null hypothesis that was actually true, which would be considered like a false positive. And these are very like mind twisting, this example that I have here, because reject a true null hypothesis would mean that we like accepted the alternative when we really shouldn't have, because that relates to this true positive. So like I might have, through my statistics, maybe I took a sample that wasn't large enough, or I had some bias in my sample. And through this framework, I said, oh, great, we found evidence to reject the null hypothesis. I found a conclusion, just going back to the silly example of like jelly beans cause acne. But really in real life, that's not the case. That would be this type 1 error of a false positive, compared to a type 2 error, which is a false negative, where we accept the null hypothesis when we actually should have rejected it. So going to one of the other examples we've talked about just tonight, if we were to say that daylight doesn't actually have a relationship with the probability of having an accident, but in reality it does, this would be an example of a type 2 error.
So basically, in like layman terms, a type 1 error is if you say someone is like, I don't know, say someone's pregnant and they're not. And the type 2 error is to say they're not pregnant and they really are.
Yep, exactly. There's some funny memes about that too online, and not funny, but I mean, I've just seen that meme exactly of the pregnancy example. So
Both can be very serious.
yeah, definitely. Yeah. No, and exactly. And thinking a little bit further on that too, depending on the scenario at hand, definitely, you know, talking in class, we've talked even about like COVID test results. Like what's the probability that you actually have COVID, given that you tested positive? That gives us back to like those Bayesian theorem too. So also thinking about like, what's the cost of a false positive? So in the pregnancy example, like you would much rather perhaps have a false positive than a false negative. Similar with like the COVID testing, you'd rather someone go and get a second test to confirm that you're not actually positive for COVID and you're not actually pregnant, compared to, you know, a false negative might be much more worse in this case.
Do we have an example of what like a type 1 error would look like in a problem?
It would be more so because we're not really bringing this back to real life. This is all very, you know, an experiment where this would be considered like our, you know, our desk validation. And we are not taking this into the field to test it, to really be able to know if the hypothesis we concluded is right or wrong. But perhaps a way that you could apply that is by, you know, taking more samples, testing again, and having more certainty that you are not making this type of error. You know, that would be a way to validate this in the field. If you were to take a totally new sample and test your hypothesis again, and if you were to see a different hypothesis than expected, then, you know, there are some concerns of a, you know, a type 1 or type 2 error. I appreciate that way of thinking too, that you would bring that up.
No problem. Thank you for clarifying.
No problem. I see a couple other questions that we would want to talk to. One is, I noticed one of the questions is, what is a p-value and how is it used? I think I know how it is used, but do not feel like I can explain what it actually is. So that is definitely, this is pretty critical to our class and it relates to distributions. So I'm going to draw on the screen to really talk about the p-value, because actually we learned about that when we were looking into like z-scores. It's pretty similar to this concept of a p-value. So if we're just trying to draw, you know, a distribution, unless I'm just drawing this of like, this is an average. Let me just think about this a little bit more. So this p-value is really getting at the tails of the distribution rather than the middle parts. Because if you had just, we're talking about like any continuous distribution and you wanted to say how far away is something from the mean, we could think of these p-values as almost like a threshold to say that this value we had is, you know, more than 3 standard deviations from the mean if this was normally distributed. So we have this symmetrical, you know, distribution, so we can apply these types of thresholds. You know, if we had a different distribution like the chi distribution or the t distribution, we just would be talking about like different shapes, you know, something like this, for example, where we would be talking about this threshold in a similar way. It's just different distributions. So this p-value is essentially trying to compare how does this value we found, something like x bar of like the sample mean, kind of relate back to what we would expect the mean to be of like the population. So we would be able to use this p-value to assess how far away, and we use the distribution and the standard deviations to understand that this is so far away from what we would expect that it is beyond this threshold of a p-value of, it's really talking about area under the curve, and it's being in this area. And that's how it relates even back to the alpha, which I think I drew that wrong. No, I drew it right the first time. Thinking about just alpha of when we are talking about, does this pass our level of significance that we would be expecting? If we wanted to say with a higher degree of certainty, we would want to say this needs to be even farther in the tail, because if we were to run a test 100 times, we want to make sure that the likelihood of the value we see is not just due to chance. And the fact that we saw something over here, if it passed, you know, if we were to say like a 99, you know, significance test, then we would be able to say this would only happen 1 out of 100 times, and due to just pure chance, but it happened, we saw it, therefore we can say the experiment we ran found a conclusion that was significant beyond this degree. So just to bring this concept a little bit more abstract, and like, why do we usually tend to have, you know, anything above 0.90 and 0.95? Because that's why I'm talking about the tails, because anything that falls into here is pretty much just expected because of how a normal distribution works and how most values really are here. And that this is nothing special of a conclusion to find. It's really only when we get to the tails that we're finding something that is extreme because it's so different from what we would expect.
I'll just talk now instead of typing in the chat. But I guess the p-value I'm talking about is, say, like the crash type in the light condition. Like if we go to that problem, I guess what is the p-value? I know we use it to compare it to alpha, but what is it exactly, I mean, telling us?
Okay. I like that. We can talk through this example perhaps a little bit beyond just what you're asking, just to set up the framework. Where if we are trying to test if, I'm just making sure, I think I'm moving around too much. Okay, so the car crash one. We're trying to test if there is any dependence between light and a crash happening. And we're trying to test this at a 1% significance level and make some type of conclusion. And the question is, what is the p-value really telling us in this example? You may know how to use it, but what is it telling us? So let's just, I don't think I ran this to have it all showing here. So I'm just going to quickly run this so we can have the data with us. So now I'm just reading in the packages, and we have this car data set, and we create this crosstab contingency table so that we can now start to compare how often when it's not head on, and was there a crash compared to daylight, you know, compared to not daylight. I believe that is what we have here. Okay, yeah, these are all car crashes. Okay. So getting to the hypothesis test, we're trying to pretty much prove that they are not independent, saying that they are dependent of each other. And we use this chi-square distribution in the similar way with what I was explaining of the normal distribution. This is just applying it to something that's not normal because of the way there isn't symmetry here. That's why we need a different type of distribution. So the p-value, I'm just going to show some of these things because we're just using this package compared to calculating it by hand, which I would also recommend just reviewing some of those steps to maybe even get a little bit further, because even when we use these packages, it almost obfuscates what's really going on under the hood. So that's why I try to, in addition to using these packages, also explain what's going on. So we see, but this does all the heavy lifting for us, and we just need to be able to interpret it. So in this case, we have this test statistic from the chi distribution using this contingency table. And this test statistic is pretty much giving us an indication of like how extreme is it. So like the larger the number or smaller, it kind of depends on the distribution and what it is we're trying to understand. So I would say for the final, if I would walk through these questions and think a little bit more about, okay, what is the test statistic for this describing? Because it's different. I linked to something like that here, because I found this to be very helpful, because it depends on the type of distribution we're using. You know, whenever we're using a z-test from the normal distribution, we have the z value of this test statistic, which again, it's all looking to see like how extreme is this value compared to what we would expect to happen. And if that p-value is small enough, that is the area under the curve of where that value fell. So let me draw again. So we have this really tiny p-value, which is saying the area under the curve is pretty much all the way over here. And if we were to have even like that 1% significance level, and let's just say like that area under the curve would be here, then what we found exceeded this threshold, so that we can say to a degree of certainty what we found passed this threshold, because the p-value was smaller than this threshold. And that's why we use this alpha. And if it's smaller than, we can have evidence to reject the null hypothesis. But if it's larger, that means that the area under the curve is over here, so that we did not find evidence and we failed to reject the null hypothesis. Did that help answer the question?
Yeah.
Great. And that's really how all these different tests are related. And it kind of comes back to just distributions and really what we learned at the beginning of the semester as it relates to a mean, standard deviations, and what your expected, outcome would be based off of the distribution. And so that's why we learned a couple of other distributions, because not everything is normal. And we want to be able to still apply these types of frameworks. Okay, so another question. Thank you, Darren, I appreciate that. Can we also speak a little on test statistics? Which I feel like we actually did a little bit.
That was me. I asked that before we just went over this, so we're good on that one as well.
Okay, perfect. How are we on time? Great. any other questions we would like to review? And also, if you, as you're reviewing this, have questions, we have a second review session on Sunday. And any questions you have, maybe we want to prepare to talk through it then as well.
One more question. I guess the problem right below this one with the Razor, Blazor, and Tracer. How come we stacked it as opposed to other problems where we don't stack them?
Yeah. We need to stack it because of how we are calculating the value for each variable we're looking at. So this is just an example of when we need to wrangle our data. And I do think if this was a more technical class, we would have focused a lot more on wrangling raw data from real life into a format that we can then test on it. But again, the scope of this class is really just the testing side, expecting clean data. So in most cases, we will have an experiment where we have for different, samples that we're taking, we have the value. And that's what we see here, and that's what you'll see on the final. It'll look exactly something like this. And we want to be able to compare. Let me even run through this a little bit more and talk through why do we need to stack it? Because it really relates more to this line of code than anything else, and even just how all of the other types of Anova tests run, because it's trying to, instead of just the head, let me show this whole thing. And even if you're making a box plot, it's trying to now see for each type of production, what would the value be? And that's really what the Anova test is getting at, is trying to compare those different things. And we need to stack it because in this case, it just makes the process more streamlined so that we can say for this, that was the value, for this, that was the value. Instead of doing a bunch of iterations, if you wanted to structure this in a different way, this just streamlines that process and makes the data in a format that we can compress into our model, which is really just trying to see the comparison this way. So even if this was in Excel and you wanted to make a pivot table, it's kind of similar to that, where we're essentially transposing the data in a way that allows us to get the numbers that we really want here, because we can't just use the raw data in its existing format. But I'm sure there's other ways to calculate the Anova that you don't need to do it this way. This is just an easy way to do it. That's a really good question to talk through, because I do think sometimes the Python makes it a little bit more challenging, but it's much better, in my opinion, than doing this by hand on paper and manually calculating all these different numbers.
Hey, Sarah, question on that stacking. Is that similar to the melting, or is that a different operation?
Yeah, I will bring up the Anova notebook because I think we had an example of both, because they're somewhat similar, and off the top of my head, I can't explain exactly how they're different. But we can talk through it perhaps with an example, because maybe they are not too different. And I think I was just testing the differences. And I feel like they're probably, different ways to get at the same thing.
Right.
In this case, but I'd be curious to know exactly how do they differ. But I would look into pretty much to just look it up and see for myself what is the key difference.
Well, I think whatever fits into the Anova call, I would think the Anova function would be obviously the best option.
Pardon, what do you mean?
Like, for example, I know that, we're using libraries to call the Anova function. There, that you had the ordinary least squares method for one of them, and then there was another one that was a little bit further down that had to do with like the full-blown Anova call for the library. And maybe they're particular to whether you stack it or you melt the data before you send it to the Anova call. Is that perhaps the reason why you stack versus melt it? I mean, is it that is either function is smart that it can tell whether or not you've stacked or melted it and it doesn't really care? Do you see my point? I want to make sure that whatever data I eventually put it into, whether it be stacked or melted, that if I send it to an Anova call or one of the Anova libraries, that it'll properly process it, right?
Right. And I know this relates to the question on Slack that I want to investigate further. That's why I haven't given an answer yet, is because I really want to look into it and compare to see. But just off the top of my head, I don't think that using melt compared to stack, as long as the data looks in this format and you call the right column based off of it, there's different ways to skin a cat.
Right.
I don't like that metaphor, but it's just off the top of my head. So as long as the input looks the same, it doesn't matter if you stack or you melt.
Right. Just feed it to the function properly. Got it.
Exactly.
I had a follow-up question. It was a little more less involved, but so it seems like what I understand of the statistics we've been learning in terms of the F distribution and the chi-squared distribution versus, let's say, the T and the normal is the F and the chi-squared are both one-tailed distributions, correct? They don't have a left tail past zero on the negative. Is that correct?
From my understanding of it, that sounds correct. I would want to double check myself on that though. I definitely know the chi-square, the F distribution. I would want to just look it up.
Yeah, no problem. And then so I'm wondering as to, for example, if you're gonna do something, let's say you have a test statistic and you're trying to find a p-value for, I don't know, just F distribution, then it doesn't really have a probability density function. You're just going to try to find the cumulative density function or the survival function, correct? I mean, there's really no, like I remember something reading from that book is that, if you do, if you have a test statistic and you get it and you pull it up in the function, it's just going to give you the right side probability from that point. It's not going to give you a point. Boy, I got to get one of these drawing things that you have. But I'm just saying, if you have a test statistic, it's going to give you everything, all the probability to the right side of something. And maybe I should review the book as well. But I just want to kind of figure out how that works. But anyway, that's all.
Yeah, I think if I'm understanding the question, can we still use like the density function for these these other distributions that don't have two tails?
Well, I think what it is that I remember in the table for, let's say, the F distribution, you're giving a test statistic or something, and then it automatically gives you the survival function for that test statistic. It gives you the probability all on the right side of that, right? But if you do it in a normal distribution, you actually have to physically call the survival function versus actually just putting in a probability mass function for that point.
Okay.
How about this? You know what? I'll rejigger my question and try to address it on Sunday. How about that?
Okay. And
Okay.
I will also look just more with the F distribution specifically. I'd say that's a weaker one in my, exhaustive knowledge of it. So I think just the question of only having positive values is kind of interesting to think about as it relates to like the why. Like, why is it only one-tailed and we don't have the two tails? So I will also do a bit more research in preparation.
Sounds good. Thank you.
Any last questions, perhaps before we wrap up tonight's session?
Can you review central limit theorem and what you'd like us to know for the final? I think I know the coding has been a struggle for some people, and so we're like focusing on the coding, but in my understanding, you want us to be writing insights based on these theories that you've listed out. And so I think having some focus on that list would really be helpful as well.
Yeah, the central limit theory is pretty important to a lot of the things that we are doing at the theoretical sense, because it gets back to, is this sample representative of the population? Because we need a large enough sample size to really know what that distribution looks like. And if you recall, there was one notebook I shared when we were just getting into distributions that actually looked into sample size. It was a simulation, and it pretty much was showing that the larger the sample you took, the closer you get to the expected value. This was way back when, and it just showed like 3 different distributions. I think it was the continuous distribution notebook. But something like that is trying to demonstrate a similar concept to when we were talking about this Plinko board. And if when we drop just one ball, you might get an outlier that's all the way over here. When you intuitively, the expected value would be, hey, it should end up somewhere in the middle. So the larger of a sample size we take and we repeat this experiment, in a sense, not repeat the experiment, but when we have a large enough sample size for this experiment, we would expect to have a better representation of the true value.
The larger the sample size, the better the representation of the true value. Am I correct about that?
Exactly. And I would just encourage you to think further as to why, just as it relates to, when we use n, which is the number of observations, kind of how does that relate to the actual kind of equations we're using? But even outside of that, just intuitively, why does a larger sample give us a higher degree of certainty?
Because we're gaining more accuracy by analyzing the data.
And I think just taking that one step further, just thinking about, what happens if our sample size is too small? What are some limitations of what we're doing, especially as it relates to bias? If we're having a small sample and it's actually biased, is that really representative of the population? So these concepts are related in a way, and it all gets down to probability, really, because that's all we're doing here is looking at probability and seeing the outcome. And is this something that we would expect to see? And that all hinges on the distribution being representative, which requires the central limit theorem to hold true, which is pretty much just saying the larger the sample is, the more we can trust that the expected value we're seeing from that distribution is representative.
Is there a percentage that's considered that provides more accuracy? If we say if our sample size is at least 40% of the larger set, we're able to have more confidence in our analysis? Is there a percentage for that?
There was actually a section in the textbook that we didn't cover. And actually, I think in the next class after this one, it'll be a lot more about designing an experiment. So that's why I didn't feel it was really, a priority for us, because I can't say there's a rule of thumb. And if you're curious, I would say check out that section of the textbook, because at the end of the day, you don't necessarily know the full population sometimes. So it's hard to give you a good answer, because I would say it depends on what it is you're looking for. I guess just one example of why I'm saying it depends of if you really have imbalanced data, and you really don't have a large sample size of something that doesn't happen that often, you know, it kind of, there's differences of like, is this sample representative enough of the population? And there'd be different tests you would want to look at to say, you know, to make that type of assessment. So in a
Okay.
roundabout answer, it depends. And there are some specific rules you can follow. We didn't cover them in this class, but there is a section in the textbook, and I assume that in the next class that focus more on like design of the experiments, that it would be more of a focus.
Okay.
Well, I hope this was helpful to the class. I'm really glad you're all here, and it was great to talk through some of these things.
Now that we have another review coming up and the information has been given to us about the final, would you like to structure the upcoming session in a similar manner, just so we know how to prepare?
I would, if new folks are joining and who didn't join tonight, you know, we might repeat some of the content we discussed today. But really, I'm hoping you come to me with questions that we can talk through, because I've prepared the content for you. So I want to know for you which concepts are still a little fuzzy that we can talk through further. So even just judging based off of our conversation tonight, perhaps I can prepare a little bit more about the test statistic and the p-value. Simpson's paradox, I think I could do a better job explaining that one. So yes, I would say come prepared with either follow-up questions, or, you know, it might be a repetition if different folks are in the room.
I have like one last question. I guess this is just relating or comparison to the midterm. In terms of like length for the coding and the technical section, how close to the midterm in terms of the length, just for time constraints and having everything kind of ready to go? Because I think you were saying that this is going to be closer to a 1-to-1 with the code that we're being given for the final review should kind of translate a little bit better than it did for the midterm.
That is true. And I will be preparing 3 hours for the technical and 3 hours for the written. So that should be a good amount of time to tackle it. But yes, the questions I have here will mirror the questions you should expect to see.
Okay, cool.
I'm not trying to give you a red herring.
Mhm.
I'm trying to prepare the class.
Okay, cool.
How many questions should we expect? Or is that still to be determined?
You can expect it to be very similar to what you're seeing in this review, perhaps with some additional questions that relate to graphing some of these things. So each, perhaps, like I listed 6 big questions, so it would likely be 6 of those, and then each would be weighted equally. And for each of those, there might be like a graphing requirement. So I'm not looking in the same way as the midterm where they were like each little component would give a point. It's more so this case study of a question, because I do feel like where we are in our class, like we really have a framework to answer specific case study questions compared to the midterm where we were kind of just diving in and didn't necessarily have that type of like structure for us to assess. So in short, I'm planning for these like 6 main questions, but there will be components within that, but it really gets back to the 10, 10 points, because I'm thinking it's going to be 60 for the technical, and this will all be finalized this weekend. So that will be what you should expect. So definitely be familiar with some graphing, because for me, I'm really going to be looking into how do you interpret it below. So if the title and axes labels are missing, that's why I want to give the 3 hours, even though I don't expect the same amount of limitations as we did for the midterm, because this will be very mirrored to the homework questions. So I don't expect it to take the full 3 hours. So I do expect more, more time into making sure you have axes labels and a caption.
So for the graph, like what we did for the midterm might be better, like having some of those codes ready to kind of put in there for like histograms or bar charts, like throwing those in there for anything we have on this, those might be useful to just kind of have ready to go.
Yeah, exactly. Like I don't plan to say like make a histogram. It's more so like visualize this as it relates to, you know, the distribution. So if that is a histogram or a bar chart or a box plot, those are probably like the three things I would say are most relevant to the types of questions we would expect. I would just have that code ready for you to use.
So will the questions kind of be, will you mix them up or will they be in chapter order?
They will be in chapter order.
Okay, thank you. That helps a lot.
No problem. And it will actually follow the sequence of what we have here in these questions.
Sorry, I wasn't able to get clarity on whether, like, when you want us to do a histogram or scatter plot, will we know which one we need to run at that point, or will we have to guess based on the question?
I don't think it matters too much. I might say, you know, make a box plot, but if you feel like a different graph would be more representative, I'm not going to penalize that decision, because I do want this to be more, you know, guided by your intuition and understanding and like what you think would be right. Because again, there really isn't like a correct thing. So I don't want to say like, do this always, because I think it's important that, you know, you take your own initiative and rationale behind it. So, you know, like don't show me a pie chart though, perhaps.
Right,
You
I
can.
know.
I mean, you can.
I heard your 20-minute lecture on why pie charts are the failure of all charts.
Well, yeah. So yeah, you can if you want to, as long as, you know, there's a good reason for it, but they're probably.
But it better show the percentages clearly.
Yeah, exactly. Yeah. Exactly. Any last questions? Okay, I will end the recording.